Okay, so good morning, everybody. We received your proposals on Friday, and the TAs have been in the task of splitting them up over the weekend. Oops. So pretty soon you'll hear from one of the TAs, and that person will serve as your TA mentor. So for the project from now on, that TA will be your kind of point of contact for questions. Of course, you can ask me any questions as well. You can ask the other TAs for that matter, but it's just easiest if you first kind of contact your TA mentor with questions from now on. So like I said, you'll find out soon who that's going to be. Some pretty interesting proposals that I saw, at least one coming through my inbox. Looks like you guys picked some fun topics. Your homework 2, I believe, is due tomorrow. And homework 1 has been graded. It's in, Mallory had it in her office, I think, on Friday of last week for pickup. Hopefully by the end of today's lecture, one of the TAs will bring them in. You guys can pick them up from me after class, just right here or just right there. And if you don't get it after class, or if we don't manage to get the homeworks here, then just go to Mallory's office from now on to pick them up. So Mallory will have your homeworks for pickup whenever. Any question about that kind of stuff, project, homeworks? No? Okay. So we're going to start our duality and optimality unit today, and it'll last 4 lectures. For those of you who have been kind of looking ahead at the lectures, you might see that I've kind of switched the next couple of lectures around on you just really recently. I decided to kind of draw out duality into a little longer section than I initially planned, because it's a pretty subtle topic, and I think it's worth going through slowly. This will be our second theoretical unit. So remember, we had our first theoretical unit was like the fundamentals of optimization unit. Then we just had algorithms. That was our first order method unit that we just finished. Now we're on to our second theoretical unit, which is optimality and duality, and we're going to use these concepts in our next algorithms unit, which is coming up on second order methods. So just to give you an idea of where we are. So what we saw last time, we went through kind of quickly, but in a sense, this isn't part of the core material of the course. I'd say that what we talked about last time is important, definitely important, but it's kind of more, it's a bit more supplementary. And we talked about some of the basics of numerical linear algebra, which will become important when we start learning second order methods pretty soon and compare them to first order methods. So just to remind you what that looked like, we went through some basic flop counts for operations. And if you have n-dimensional vectors and matrices, then it looks like the following. Vector-vector operations, like adding together 2 vectors, taking an inner product between 2 vectors, multiplying a vector by a scalar. That was on the order of n flops. Matrix vector multiplication was on the order of n squared flops. Matrix-matrix multiplication was on the order of n cubed flops. And solving a full linear system was also on the order of n cubed flops. So this one, by the way, I think surprises some people when they see them compared side by side. But in terms of flop counts, that's really those are really the orders of those 2 calculations. If you're doing operations with banded or sparse matrices, then you can do these a lot more efficiently. And you basically just look at all of these counts involving matrices and reduce them by an order of magnitude. So that's when the bandwidth is constant, or the number of elements in your matrix is of linear order with n. So matrix vector multiplication would for example, become linear, not quadratic, if I had a banded matrix. And all these get reduced as well. So why do we care about linear systems? It's because they arise very frequently in optimization. And the context in which we see them is when we try to minimize a quadratic function. For example, least squares problems. Why is minimizing a quadratic so kind of fundamental to optimization? Why is that such a special object, quadratic? Well, if you think about where we came from, first order methods do a quadratic approximation at every step, right? The quadratic form is actually the identity. So it's kind of a trivial quadratic. Second order methods do a quadratic approximation, but they use the Hessian of the criterion function instead of just the identity for the quadratic form. So because we make quadratic approximations internally in a lot of our kind of algorithmic procedures, we frequently see linear systems in optimization. It's kind of one of the core computational units that we have to figure out. And so we talked about two different ways of solving linear systems, or least squares problems in particular. And they were, one was using the Cholesky decomposition, and the other was using the QR decomposition. And just to remind you, so suppose we're solving a least squares problem in a matrix capital X. The Cholesky decomposition acts on X transpose X directly. It forms that matrix, and then it factorizes that matrix. The QR decomposition acts on X only, not on X transpose X. So what are the trade-offs here? Cholesky decomposition ends up being cheaper and uses less memory. Both of these are true by nearly a factor of 2. So it's nearly twice as fast and uses half as much memory. But it's more sensitive to numerical errors. We didn't talk about why that's true, but go back to the notes if you want to see kind of precisely why that's true. It's because it's forming X transpose X, whose condition number is the square of that of X. The QR decomposition is more expensive and uses more memory, but on the other hand, it's more robust to numerical errors. So it depends on your application. If you think that the quadratic you're trying to minimize is perhaps poorly conditioned, which means it has a very largest eigenvalue and a very smallest eigenvalue, or singular value, then you may want to use a QR decomposition and sacrifice a little bit of speed and memory. Okay. Any questions about that? So we're going to leave the algorithm first-order method world behind now, and we're going to go into duality and optimality. And this is one of my favorite topics in the course. I think duality is a really cool topic. And the arguments are all very simple. These are not complicated mathematical arguments we're going to go through, but you can see they end up being very powerful. So we're going to start off with learning duality in linear programs only. So that's what we're going to spend the whole day today talking about, duality in linear programs. If we finish early, we may start on duality in general. We'll skip ahead to the next lecture, but I don't think we'll do that. So for now, suppose that we just wanted to find a lower bound on the optimal value of our linear program. Okay, so we're minimizing some function f. This is the goal behind duality in general, minimizing some function f. We want to find a lower bound on its optimal value. We want to find some b such that b is less than or equal to the optimal criterion value. Just trust me for why I want to do this for now. It may seem like a little bit abstract, but you'll see why I want to do this very soon. So let's consider the following very simple linear program in two variables. X and y are both real valued here. I want to minimize x plus y, subject to the constraint that x plus y is bigger than or equal to 2, and x and y are both non-negative. What's a lower bound for that linear program? For the optimal value of this linear program? It's just 2, right? It's kind of, there's almost no argument here. One of the constraints is that x plus y is bigger than or equal to 2. So if this is true of any feasible point, then the solution must satisfy this as well. And so a lower bound on the optimal value is just 2. Okay? Just stare at that for a second, because it may be so obvious that it seems confusing or something, but that's all the point I'm trying to get across. One of the constraints says x plus y is bigger than or equal to 2, so clearly at optimality we have to have x star plus y star being bigger than or equal to 2 as well. Therefore, 2 is a lower bound on the optimal value of our linear program. So you may say, okay, well, we just got lucky, right? Because I set up this problem. I wrote down the constraints and the criterion, and I made sure that one of the constraints was x plus y is bigger than or equal to something. I made sure that the criterion was that same thing, x plus y, so maybe we got lucky. So let's try another one. Let's try the top one. And it helps to work this out on paper. So let's suppose we're trying to minimize the criterion x plus 3y. And we're going to be subject to the constraint that, same constraints, x plus y is bigger than or equal to 2, and x and y are both non-negative. So how do I find an optimal bound a lower bound on the optimal value of this linear program. What do I do here? Any thoughts? I want to somehow get out of the constraints something that looks like x plus 3y is bigger than or equal to something. These are all linear constraints. Okay, well here's, yeah, what do you think, Logan? Exactly. So we're just going to, we can always multiply this guy by 2, for example. That's a valid constraint. And I can add this to x plus y bigger than or equal to 2. So I can generate a constraint that looks like x plus 3y is bigger than or equal to 2 plus 0, which is just 2. Right? This is a valid constraint given these constraints. This is always true of any feasible point. So at the solution, we again see that x plus 3y has to be bigger than or equal to 2. So the bound is b equals 2 again. Okay, let's just try another one. If I put down px plus qy, and I put down x plus y is bigger than or equal to 2, x is greater than or equal to 0, and y is greater than or equal to 0. P and q are arbitrary now, arbitrary scalars. They're not variables, they're just constants. So I'm going to play the same game. I'm going to multiply this by some number a, but a has to be positive or non-negative, right? Because if a was negative, it would flip the sign of this inequality. So I'm going to multiply these by numbers and then add them together, and I want to make sure that I keep the directions of the inequalities the same. Otherwise, it wouldn't make sense to add them together. So I'm going to restrict a to be non-negative. I'll multiply this by, then multiply each of these constraints by a, b, and c. I'm going to generate constraints that look like this. ax plus ay is bigger than or equal to 2a. Bx is bigger than or equal to 0, and cy is bigger than or equal to 0. And now what can I do? I can add all these together, right? And I can get constraints that look like a plus b times x plus a plus c times y is greater than or equal to 2a. Right? Just by adding those three together. And now I want to make a plus b equal p and a plus c equals q. Because if I were able to do that, if I were able to choose a and b and c such that a plus b is p and a plus c is q, then this would look like px plus qy is bigger than or equal to 2a. And so I would get a lower bound on my criterion function at optimality. Right? Is everyone following? So therefore, we can say that the bound is b equals 2a for any a, b, and c such that a plus b is p, a plus c is q, and a, b, and c are all non-negative. Right, we get a lower bound of 2a for any such triplet ABC. Questions about that? Yeah.
This is not a strict lower bound, right? Because when we were minimizing x plus y, we can never get less than 2, but here we can get greater than 2. So it could be a real lower bound, right?
What was the last sentence? There could be a...
The real lower bound could be larger than 2 in the first example.
Well, I mean, there's no real lower bound. They're all lower bounds. Right? But you're saying the biggest lower bound could be something that's tight. Maybe it's equal to the optimal value of x plus 3y. Maybe, yeah. That's a very good insight. That's kind of part of the reason why we're doing this. And in fact, this leads into the next thing we're going to look at, which is what's the best lower bound we can get? What's the biggest lower bound? Right, any of these serve as a lower bound. Any a, b, and c give us a valid lower bound on the criterion p plus qy, optimality. But what if we want the biggest lower bound? We want the kind of tightest statement we can make. Then we're going to maximize this quantity. Right? So we're going to say just take the max. Of 2a, subject to the following constraints. A plus b is p, a plus c is q, a, b, and c are all bigger than or equal to 0. And this is going to be, so if we take b equals the maximum of that, the maximum of 2a subject to these constraints, this is the largest lower bound. Largest or the tightest lower bound. So let's just make a few observations. What is this? What did I write down here? That's just a linear program. So we started off with a linear program, this one. We tried to find the biggest lower bound for its criterion value. We ended up with a second linear program. Okay, so that's interesting. So we call this the dual linear program to this linear program. And in that context, we call this the primal linear program. So the primal, or the original linear program, is this one. The dual we just derived is this one. It produces for us the largest lower bound possible on the optimal criterion value. So we know, just from construction, that if I were to call the optimal value here A, and I were to call this capital B, by construction, we have A is bigger than or equal to B. That's the way we constructed B. How many people here think that at optimality, we're going to get an equality here? So if I actually were to solve this linear program and solve this one, that we get A equals B. Raise your hand. How many people think that I'll get a strict inequality? So A will be strictly larger than B. How many people think it depends on what A, B, C, what P and Q are? Okay. So in a sense, the people who said that we always get equality are right. We always do get equality, except in very peculiar situations. So the answer is actually it depends. But as you'll see later on, we almost never encounter those problems in practice. So now let me test your intuition even further. What happens if, for example, there's no such A, B, and C I can find that are all positive or non-negative, such that A plus B is P and A plus C is Q? What happens if this constraint set is empty? Yeah?
That would suggest that either P or Q is negative, and so there is no lower bound.
Okay, well, so what happens, if, for example, if P is negative? Took P to be minus 1. Think about it in two ways. First of all, what's the optimal value of this linear program? Minus infinity, right. So if we're maximizing over a constraint that's empty, then we take that value to be minus infinity. Just like if we're minimizing over a constraint that's empty, we take that value to be infinity. Does that make sense up here? If P was negative, look at this problem. small can I make A? I can make A equal to minus infinity, right? Because there's no bound on how large I can take, for example, x to be. I could just take x larger and larger and larger, and this would be smaller and smaller and smaller, and so the optimal value of this program would also be minus infinity. Okay, so that didn't break anything. It is a valid lower bound. We just get that b is minus infinity, and a was also minus infinity. Okay, let's keep going. Let's try one more. I'm just going to change the constraints a bit. So now I'm minimizing px plus qy again, subject to x being bigger than or equal to 0, y being less than or equal to 1, and 3x plus y being equal to 2. So how do I handle that one? I'm going to introduce multipliers again. And these multipliers we call dual variables for exactly the reason that they are going to form a dual problem for us eventually. So I'm going to introduce 3 dual variables. Here I'll introduce a. It's going to be positive. What do I have to do here? I'm going to eventually add multiples of these constraints together. This one has the opposite direction to this one, so what am I have to do here? How do I cope with the fact this is less than or equal to 1 instead of bigger than or equal to something? Right, I can multiply by some b that's negative. That actually ends up being a little bit more hard to keep track of. It's completely equivalent, right? I could do that. But I'm actually multiplying by some b that's positive, and instead just change this to be minus y is bigger than or equal to minus 1. It's easier to keep track of that way. I'm going to multiply this by some dual variable c. Do I have any restrictions on what c can be, positive or negative? I don't, right? Because this is an equality. So whether or not I multiply by something positive or negative, it's always an equality. So now I'm going to add all these 3 together, right? And what do I get? Do the same thing. I get ax bigger than or equal to 0. This one gives me minus by is bigger than or equal to minus 1. And this gives me 3cx plus cy is equal to 2c. And if I add them all together, I get a plus 3c times x plus minus b plus c times y is bigger than or equal to 0 plus, this should have been minus b, plus 2c. And I want to make this equal to p and not equal to q. Right, so now my dual problem, this is just more practice with dual problems, is to maximize this lower bound, minus b plus 2c, subject to the constraints that a plus 3c equals p, minus b plus c equals q, and a, b, and c are all, actually, a and b are non-negative with no constraint on c. So again, whatever the value of this program is, this linear program, it's going to be smaller than or equal to the value of this linear program just by construction. How many dual variables do I have in general? I have one dual variable for every constraint, right? Because we introduced one for each constraint. And the ones that correspond to inequality constraints, I'm always going to transform those to be bigger than or equal to something. Those will give me dual variables that have the constraints that they should be non-negative. And the dual variables that correspond to equality constraints, I have no constraints on them, because I can always add equality constraints. Because I can always multiply an equality constraint by a positive or negative number, and it's always still an equality. Okay, I think this kind of manual construction of dual problems really gives you an idea of where they come from. And so today we're going to talk about duality for a general form LP. we're going to construct for an LP in standard form, essentially, or close to standard form, its dual. I'm going to give you some examples of them. The two examples I'm going to talk about are max-fill and min-cut, which is an interesting example you guys may have seen in other classes. We'll do a take on it from the perspective of duality today. And then also a minimax matrix games example. There's another way to derive duals, which we're going to also learn halfway through, which is different. It's formally different, but it's completely equivalent to the one I showed you for linear programs. So for linear programs, you kind of have two ways. You can pick how you want to do it. The way we just did, which is kind of like a manual construction, or the second way, which we call Lagrange duality. But it's important to learn the second way because beyond linear programs, this manual construction is not really going to work. Was there a question?
Yeah, it's not obvious why you would typically end up with inequality instead of a lower bound when you get the when you solve the dual problem. So can you give some information about why you end up with an inequality in most cases?
Let's hold off on that until we talk about Lagrange duality. So when we talk about Lagrange duality, we'll talk exactly about when that happens. So that phenomenon is called strong duality. We're going to see in both of the examples today that we have strong duality in these two linear programs that we care about. So you'll see for max-fill, min-cut, and for this matrix games example, we have strong duality. And it turns out that it happens very often. It's a fair question, though. Okay, let's take a general form LP. It's actually not standard form, but I prefer looking at this form. And we're going to minimize some linear function, right? C transpose x. Now x is an n-dimensional optimization variable. It's not real valued anymore. Subject to the following constraints: ax equals b, and gx is less than or equal to h. So this is a completely general linear program, right? You can write any linear program in this fashion. And I'm going to introduce two blocks of dual variables. Each of these are themselves multidimensional. So u and v. And u is going to be a dual variable that's of dimension equal to the number of rows in A. So let's suppose that A was m by n, and g was, I think I said r, r by n. And so then x is going to be n-dimensional. U is going to be m-dimensional, and v is going to be r-dimensional. And we're going to put a constraint on v that has to be non-negative in every component. To introduce those two blocks of dual variables, just like we did before. Just introducing a dual variable for every constraint. Right? This is actually m constraints. It's ai transpose x is equal to bi for every I between 1 and m. This is, again, it's actually r constraints. I'm just introducing a dual variable for each one of the constraints. And now I'm going to do the same game, which is that I'm going to say I can take u, and I can multiply every component of this equation by the corresponding component of u, and that's still an equality. Right? So I can always do, it's always true that u transpose ax is equal to u transpose b. And again, I can always multiply every component of this inequality by the corresponding component of v, as long as v is non-negative, and it's still an inequality. So I can always say that v transpose gx is less than or equal to v transpose h. Those are my constraints on v, that it's non-negative in every component. And now adding them together, what do I get? I'm going to just rearrange it. I get u transpose ax minus b plus v transpose gx minus h is less than or equal to 0. And I want to make this look like c transpose x is bigger than or equal to something, because I want a lower bound on my criterion value, c transpose x. So let's just pull out everything that multiplies x. Right? That looks like a transpose u plus g transpose v transpose x And what's left over is B transpose U and H transpose V is less than or equal to 0. And if I rearrange this, it just says that minus A transpose U minus G transpose V transpose X is bigger than or equal to minus B transpose U minus H transpose V. So if I were able to choose U and V so that this was equal to C, then I would have this being C transpose X is bigger than or equal to something, and this would serve as my lower bound. And so the largest lower bound I can choose is minus B transpose U minus H transpose Z, subject to the constraint that minus A transpose U minus G transpose V is equal to C, and V is non-negative. No constraint on U. So this is called the dual LP. It is a linear program, right? My variables are U and V. So just to be clear, I'm maximizing this over U and V. This I'm minimizing over X. And this guy was the primal LP. Okay, and by construction, again, we know that the value of this linear program is the optimal value is less than or equal to the value of this one. So this is, I don't have a better name for it than the manual way of constructing the dual, right? We actually go in and we assign a dual variable to every inequality. We rearrange it until we get something that looks like a lower bound, and then we just force whatever multiplies X to be equal to what we need it to equal so that we get a lower bound on the criterion value from the primal. Right? The arguments are completely straightforward. There's nothing fancy here mathematically. It's just maybe not something that you would have seen before. Questions about that? Okay. So here's a nice example about where the primal and dual have different meanings and are interesting in their own right. And we'll see another one at the end of the class. And that's max flow and min cut. How many people have seen this in another class, like a CS algorithms class or something? I expected more people to have seen max flow and min cut, but it doesn't matter. We'll go through it anyways. So there's a nice history on max flow and min cut. Turns out people cared about this a lot around the time of, I think it was World War I, although I could be mistaken. It could have been World War II. But there's a lot of history of these problems that's very interesting. People didn't know they were duals for a while. So people were actually trying to solve max flow. Other people were trying to solve min cut. It turns out that they're actually duals of each other. So in some sense, solving one is equivalent to solving the other. But initially, when they were posed, people didn't know that because they're both interesting in their own right. They both kind of have different meanings. So here's a description of the max flow problem. Suppose we're given a directed graph. So I just drew a graph here on the slide. It has vertices or nodes V. It has edges E, and E is directed. So from every edge has a given direction, right? It points from one node to the other. And we're going to define a flow over the nodes of this graph. The flow is just going to be a vector that takes values over the nodes of this graph. So over the edges of this graph. So for every edge ij, the flow fij it's the corresponding component of the flow f over that edge. And it really just mathematically describes the notion of a flow that you might think of naturally. We're going to pick two nodes in the graph, and we're going to label them the source and the sink. So S is the source and T is the sink. So we're going to talk about sending a flow from S to T. And so I've drawn S and T in this graph. And the flow is defined as follows. So first of all, the flow has to be non-negative over every directed edge. Right? So we only have directed edges in this example. If I look at the value of the flow from, say, S to this node, it has to be non-negative. It's just our definition of the flow. And it's also upper bounded by some capacity, Cij. So this you can think of as the capacity of the channel that's described by this edge. Maybe we have to have some amount of non-negative flow It can be 0, but it can't be any more than this number, Cij. And Cij is a constant here. Those are just constants that are given to us with the graph. And this is the kind of fundamental property of the flow, which is that if you look at the flow going into any node k, so I've fixed some k here. That's not the source of the sink. Suppose this is k. And I add up the flow going into k. So that's the flow coming from S, the flow coming from this node, the flow coming from that node. That's the flow going into k. It has to equal the flow leaving k. So that has to be the same as the sum of the flows leaving k. The only edge that leaves k is this one. So what we've said is that the value of this, the flow we assign to this edge, has to be equal to the sum of the flows across these three edges. It's kind of like a conservation principle for the flow. That's true for every internal node in the graph. It's not true for the source of the sink, because we're thinking about the flow as emanating from S and terminating in T, so we don't have any kind of conservation concepts there. So the max flow problem is to find the flow, so to find the vector f that satisfies these constraints, that maximizes the total value of the flow from S to T. You can see why this may be important, for example, for traffic planning, things like that. People cared about this problem. People still care about this problem. And what's the value of the flow from S to T? Well, because of this kind of conservation principle, the total value of the flow from S to T is just the total value of the flow leaving S. Because then we can't add any flow once we've left S. It's going to add up to exactly what happens. Each node, the flow entering equals the flow exiting. So the total flow is just going to be the total amount that we're able to send from S. So the problem is to find the vector f that lives on the edges of this graph, satisfies all these constraints, and achieves the maximal value of the sum across, in this case, these four edges. Add up the flows leaving S. So that's the sum of fSj for all edges S, j. It's the max flow problem. Let's go and derive its dual. Okay, let's see if we can apply the same principles we learned to this problem. It's a little bit different than what we saw, because the primal now is a maximization problem, not a minimization problem. So its dual is going to serve as what? It's going to serve as a lower bound. As an upper bound on the optimal value of this linear program, not as a lower bound, right? It's just the reverse of what we saw before, but aside from that, it's completely analogous. So I'm going to get started and write everything in a form that we can apply our logic to. So I'm going to change around this constraint, which said Fij is less than or equal to Cij. Just flip it around so we can use it. And this last constraint was Fik equals Fkj for all k not equal to S or T. This was for all ij. And this was the sum over I, k that were edges, and the sum over k, j that were edges. Okay, so let's introduce dual variables. I believe, just want to check I don't mess the notation up. Yeah, I called these okay, so here it's going to be actually more convenient to write all these as lower bounds, which is fine. That's actually how we had it in the last formula for the general form LPs. And it's just more convenient to write this as in this form. So minus Fij is less than or equal to 0, and Fij minus Cij is less than or equal to 0. I'm going to introduce dual variables Aij here and Bij here. They're both going to be non-negative. I'm going to introduce, for each one of these constraints, I'm going to introduce the dual variable xk. There's no constraint on xk, right, because it's an equality constraint. So what is the possible combinations of, now it's upper bounds we can create by multiplying these constraints by these dual variables? Well, we get something that looks like this. Minus Aij times Fij plus Bij times Fij minus Cij. That's the sum over all I and j that are edges, plus the sum over all k that are not equal to s or t of xk times the sum of fik minus fkj. This whole thing is less than or equal to 0 for any valid combination of aij's, bij's, and xk's. Right? Because this thing is less than or equal to 0, this thing is less than or equal to 0, this thing is equal to 0. So this whole thing is less than or equal to 0. So now the strategy is to rearrange this so we get something that looks like the sum of fsj is less than or equal to something. And that something will serve as our upper bound. So we're just repeating the steps that we learned in simpler problems for the dual construction. Okay, so let's collect terms now. And we're going to write this as the sum over all I and j. What's the variable here in an optimization problem? It's f's, right? F is the variable. We're going to collect terms that look like m, I called it ij, times fij. So everything that multiplies one of the f's, we're going to collect into this term m. And we're going to say that's less than or equal to something. What terms here don't involve our primal variables f? It's just this one, right? So it's less than or equal to the sum of bij, cij. So I've not done anything clever so far. All I've done is introduce some notation. Now we have to figure out what these leading terms mij look like. So I claim that if we look at all the terms that start with m, s, j, so when do we ever have f, s, j in this this inequality here? Well, we can get it if we have an asj here, so it's minus asj. And then this would have to be plus bsj. Can we ever get an fsj in this expression here? So k can't be s, but can we ever get an fsj? We can if I was s and k was j. If we're looking at the flow going from s to k, in the particular case that was k was j. So what do we get for that? What multiplies that particular term? It's just going to be xj. Right? Because this would be fsj times xj. Okay, let's look at the reciprocal terms, which is mit. And it's the same concept. This would be minus ait. This would be plus, no, that's right, plus bit. And again, we ask ourselves, how can we get something multiplying fit in this expression? Well, we can't get anything out of this term because k can never be t. But we can get something out of this term if k was I and j was t. And so we get minus x I. Okay, and then the generic term, when both I and j are, so I have I not equal to s and j not equal to t in this guy. This just equals mij is equal to aij plus bij minus I think it looks it. Yeah, we have the same terms, xi and xj. Right, because for mij here, I just take k to be j, so I get an xi. I get an positive xj term. And here, to make this fij, I take k to be I, and I get a minus xi. Okay, so now we figured out, just by kind of inspecting this inequality, what these different terms have to be that we've collected into our big linear combination of fij's. And we want to form a lower bound on the sum of fsj. That was the goal, right? That was our criterion value. So, in other words, in this sum, we only want to ever see terms that look like msj, and everything else we want to be equal to 0. So we want this equal to 0. We want this equal to 0. And we want this equal to 1. Right? Because if this equals 1, then we're summing up fsj times 1. And then every other term here, mij, is 0. And that would give us the proper upper bound in our criterion function. Okay, so now we're able to write down the dual problem, which is going to be the smallest value we can make this upper bound. Where we have variables a, b, and x subject to the constraints that we have to have bsj minus asj plus xj is equal to 1 for all j, such that s and j are an edge. We have to have bit minus ait minus xi equals 0 for all I. We have to have minus, just writing the b's first, bij minus aij plus, I'll just write it like this, minus xi plus xj equals 0 for all ij, such that, I was not s and j was not t. So now I've written down almost the dual problem. The constraints I need to put down are that a and b are both non-negative. There's no constraint on x. So this is the dual to the max flow problem. So the linear program, we already know that because we know that the dual of linear programs are linear programs from our general form calculation. We're almost at something interpretable, but I want to get rid of the variable a, because you can see it kind of serves as a slack variable. So we don't need it. So in particular, I can rewrite this as bsj is bigger than or equal to, or bsj minus xj is bigger than or equal to I can always rewrite this constraint like this. bsj plus xj is equal to 1 minus asj, or 1 plus asj. And since asj is non-negative, this has to be just less than or equal to 1. And I can do the same thing here everywhere, right? Bit minus xa is less than or equal to wait, do I have the signs right way? Oh. No, I have the signs right. So less than or equal to this line? Right, sorry. Yeah, of course. Since a is non-negative, it has to be bigger than or equal to 1. Right, this is equal to ait, which is bigger than or equal to 0. And the last line looks like bij minus xi plus xj is equal to aij, which is bigger than or equal to 0. Thanks, of course. So these are all sort of slack variables, and so I can actually eliminate them by just taking these inequalities instead of these equalities. So you've learned that kind of towards the start. And so what do I do when I get that? I claim that I get the following program. Minimize over all b and x of the same criterion, subject to the constraints that I'm just going to write it as bij plus xj minus xi is bigger than or equal to 0. B is non-negative. So I'm going to actually capture both of these two constraints by introducing kind of two more components of x. Right? X only lives on all the nodes except for the source and the sink. That's what kind of makes these two equations a bit exceptional. But if we introduce something like this, I guess I have it backwards. Yeah, I have it backwards. Then we can capture all these constraints just by writing this for all I and j. Right? Above, this was true for all I and j, where I is not equal to s and j is not equal to t. If I introduce, just for kind of notational convenience, these two additional components, then when I is s, this looks like bij plus xj minus 1 is bigger than or equal to 0, and that just gives us this constraint. bsj plus xj is bigger than or equal to 1, and the same for the middle constraint. Okay, so this is equivalent. These two problems are the same. All I did was remove a slack variable. That's also the dual LP. Okay, now this should start to look a bit familiar if you've seen min-cut before. Are there questions before we go to min-cut? So this calculation, it wasn't terribly challenging, right? It's just detail. That was all it was. It's just the details of going through the dual construction. The concept is exactly the same as what we did in these simple cases with two variables. It's just that now there was more variables to worry about. So there was nothing really challenging or intricate. It was just a matter of kind of turning the crank, going through the motions for this dual problem. So this is our problem. I said that this was the dual problem. And now when we look at it, we can see this is almost the same as a min-cut problem, but not quite. Because min-cut is not actually a linear program. Min-cut's an integer program. And let's just suppose that at the solution, so at the dual solution, we had x, I guess I call it just xi, is either 0 or 1 for all I, for all of the nodes in the graph. So that's kind of a relaxation of this problem, because in this problem you can see actually we have the constraint implicitly that all of the values of x have to be between 0 or 1, but never equal to 0 or 1. So let's just suppose that we were lucky and we ended up solving the dual and we got that all the x's were either 0 or 1. If we were lucky, that might have happened. Then we're going to define two sets. We're going to define A to be the set of all nodes I, such that xi was 1, and B to be the set of all nodes j, such that xj was 0. And if you look at the picture in the graph, I've just circled, for example, in blue, this blue kind of shaded blob, suppose was the set A. It was all the nodes for which we solved the dual, we got lucky, and the values of the dual variable x were all 1 on those nodes. Then if you look at this constraint, right, this constraint up here, then bij being bigger than or equal to xi minus xj, in this case, then that tells us that we're going to have bij being equal to 1 if I was in A and j was in B, and it's equal to 0 otherwise. Right? Because we're trying to, in the dual problem, we're trying to minimize a sum of costs. If I was in A and j was in B, then xi was 1 and xj was 0, so this is 1. So we have bij is bigger than or equal to 1. That's our constraint. And we're trying to minimize the sum of costs, so we just take bij equal to 1 to make this term as small as possible. Otherwise, we would have this being equal to 0, right? If they're both in A, it's equal to 0. If they're both in B, it's equal to 0. So we have the constraint that bij has to be bigger than or equal to 0. And again, if we're trying to minimize the sum of capacities or costs, we just would take bij being equal to 0. So if we were lucky and we happened to get that x at the solution was all binary, then so would B. And we would see that exactly B defines what we might call a cut over the graph. And actually, A and B define the cut over the graph. And this criterion value it equals the value of the cut. Defined by the pair AB. So look back at the picture. Suppose this was equal to A and this is equal to B. We look at all the edges that leave A and go to B. So that's this edge, and that edge. And remember, B is going to be 1 on all of these three edges, and it's going to be 0 everywhere else. So the criterion, which is the sum of bij, cij, is just the sum of these three capacitors and these three edges. And that's just equal to, that's by the definition of a graph cut, that's equal to the value of the cut between A and B. It's the sum of the cost of edges leaving A and entering B. So we've argued that if we were to relax the dual problem by taking xi to be, or not relax, actually if we were to further constrain the dual problem by taking xi to be binary, then we get the min-cut problem. So in other words, we've said that the dual is the LP relaxation of the min-cut problem. The min-cut problem forcing all of x, all the components of x and b to be binary. Our dual problem doesn't have this constraint. It just forces them to all between 0 and 1, essentially. Those constraints are implicit there. So the dual is intimately related to the min-cut problem. And now something that you might have recalled from another class where you studied max flow and min-cut in detail is that there's something called the max flow min-cut theorem. The hierarchy we've established so far is that the value of the max flow is less than or equal to the optimal value for the LP relaxed min-cut. That was just the dual LP we derived. By construction, this was always going to be an upper bound on the value of the max flow. That just comes from duality. That's this first equality. Because that's a relaxation of the integer program, right, and it's a minimization problem, we can always achieve a lower value than we could if we further constrained the variables to be binary. That's what the second inequality comes from. So the dual LP is always going to be less than or equal to the capacity of the min-cut if we actually solve this integer program. This is non-convex, by the way, right? We don't know how to solve integer programs, at least not so far in this class. It's a very famous result called max flow min-cut, which says that actually the right-hand side here and the very left-hand side are equal. So the value of the max flow is equal to the capacity of the min-cut in any graph. That tells us that actually all these inequalities are equalities. So it tells us two interesting things. One, which is not really the point of this exercise, which was that this relaxation is tight. This convex relaxation of this non-convex program, the min-cut integer program, if we relax it to an LP, it's actually tight. So that means that at the solution, we will generically have, if we solve the LP, we will generically find x to be either 0 or 1. It's kind of interesting. And the other thing it tells us, which is the more kind of relevant part of this exercise, was that the optimal value of the dual LP is equal to the optimal value of the primal LP. So at optimality, the dual LP gives us the tightest upper bound. That upper bound actually equals the value of the max flow in this exercise. Okay, so when we drive the dual and we get a bound that's tight, we call that strong duality. And we're going to be kind of interested to know when that happens. We're going to be interested to know when that happens because we're going to see in the next class that when that happens, we can actually get more than just a matching criterion values. We can actually get often an expression for, say, the primal solution in terms of the dual solution, or vice versa. That's the more interesting part, is how the solutions relate. The fact that the criterion values are equal is kind of a first step to getting to that second, more interesting equivalence. So I think the intuition that we talked about so far was that this happens pretty often for linear programs. We're going to see a very precise answer to how often this happens when we talk about Lagrange duality next time. So we'll get more soon on how often strong duality happens. Any questions about this example, max flow min cut? Yeah. Do I have to specify that Bij is bigger than or equal to 0?
Say x I equals 0 and xj equals 1.
Are we talking about on the slide, or?
Yeah, that one.
Well, Bij is always, it's 0 or 1, so it's always bigger than or equal to 0. This means that all three of these have the constraint that are either 0 or 1. Yeah?
So why did you decide that A is a slave variable but not X?
Well, let's look back at this. How could we eliminate X from these constraints? I'm not sure I know how to do that. I mean, just from a very kind of heuristic standpoint, there are many more A's than there are X's, right? X's live on the nodes, A's live on the edges. So it seems like it would be hard to eliminate X. It's more likely that A is what's superfluous.
So what is the definition of a slack variable?
Well, so there can be many slack variables for a particular problem, right? I think actually here we could have eliminated, no, we couldn't have eliminated B because it appears in the criterion. That's why. So with respect to the constraint, it seems like A and B have symmetric roles, but B appeared in the criterion, A didn't. So I couldn't have eliminated B. A slack variable, it's not terribly well defined. When we talked about kind of the transformations for convex programs in the third lecture or something, we defined a slack variable as something that only plays a role in the following kind of inequality, right? If we have a slack variable, if we have an equality that looks like, f of x is, well, I guess for any equality it has to be a linear function, right? A transpose x is equal to some constant, say b plus y, and y was non-negative, then y plays the role of a slack variable here, because we can always say that this is, if y appeared nowhere else in this expression, then this is completely equivalent to saying that ax is bigger than or equal to b. Right, these two together.
So what X is not bounded, and then we wouldn't be able to do this if we remove X, right?
Here?
Yeah.
Yeah, we couldn't. That's true. We couldn't do that with x because at least as far as these expressions go, we don't have a, x came from the equality constraint. We didn't have a positivity or non-negativity constraint on x. Other questions? Yeah, Jersey.
In terms of interpretation of the min-cut problem, is that like finding the bottleneck in the flow? Is that how you think about that in practical terms?
Finding the bottleneck.
The set of edges that have the lowest capacity in mind. Just trying to decide back to the train.
Yeah. So you want the cut to be as small as possible, right? The capacity of the cut to be as small as possible. So it's kind of a place where the flow maybe is the most distributed across the boundary nodes for the cut. You want to separate the nodes into two pieces where you kind of do the least amount of damage in terms of the flow that crosses through from A to B. But max cut is another problem people are interested in. Max cut would be the adversarial version of this, which is you want to kind of damage one's network as much as possible by separating into two. Max cut's actually NP hard, as far as I know. So it's an interesting distinction from min cut, which min cut is a non-convex program. It's an integer program, so you may think it's NP hard, but we know actually that it's equivalent to max flow in this sense. So we can solve linear programs in polynomial time. Okay, let's take a quick couple-minute break, and then we'll finish off with, we have one more example to go. Hopefully you guys can remember this way of deriving duals for LPs. So I think that the way we talked about so far was pretty natural in the sense that you can, if I give you an LP, say on the homework, or even worse on the midterm, you could just remember that you introduce dual variables, you play around with the constraints by adding them together until you get the criterion value, and then that serves as a bound, whatever you get out of that kind of game that you play. And if you start off with a minimization problem, then you wanted to get the biggest lower bound possible, so you maximize that across all combinations of dual variables. I think it's a pretty natural construction. That's why we talked about this first. There's a problem with it, though, which you can probably guess. How do we get this to work for general convex problems? Let's suppose that our criterion was quadratic and our constraints were linear. How do I play around with linear constraints to get a lower bound on a quadratic? Not that easy, right? Or if the criterion were just some kind of convex function, how do I play around with constraints that are composed of arbitrary other convex functions to get a lower bound on that one? It's not so easy. So that's the roadblock in this this particular perspective on duality. Fortunately for us, there's a completely equivalent second take on duality, and that's called Lagrange duality. It gives you the exact same dual for linear programs, but it extends to general programs, and in fact, it even extends to non-convex problems. We'll talk about Lagrange duality next time. I'm just going to introduce it for you now. We're going to quickly talk about it, and then we're going to talk about an example with it. I actually think the calculations with it are a lot easier than they are with the linear program we just learned. I think that they're less messy, for sure. It's just kind of less obvious where it comes from. The one with linear programs came from adding things together to get the right bound. So remember, we already saw this. This was for a general form LP. We call it the primal. This was its dual. We wrote that down. We derived it, even. Here's a second explanation for where this thing comes from, and it follows what we call Lagrange duality. And again, we're going to introduce a dual variable for each set of constraints. And so we'll introduce the dual variable here, u, and the dual variable here, v. And look at this first line. We say that if u is anything and v is non-negative, like we usually require it to be, and x is feasible, which means that x satisfies these constraints, then the criterion C transpose x is always bigger than or equal to the following: C transpose x plus, and this is where we get what looks like Lagrange multiplier terms, u transpose ax minus b plus v transpose gx minus h. Why is that true? If x was feasible, then this is equal to 0, x minus b. So I could take u to be anything. This term's always going to be 0. If x was feasible, then this thing is component-wise going to be less than or equal to 0. Right? Gx minus h is less than or equal to 0 in each component. If I take the inner product of that with something whose components are all non-negative, this is the sum of vi times gi transpose x minus hi, all these terms are also less than or equal to 0. So I add them up and they're still less than or equal to 0. So again, for feasible x less than or equal to 0, inner product something bigger than or equal to 0 gives you something less than or equal to 0. So this bound always holds. This is kind of the key step in forming the Lagrangian. In fact, we call this quantity on the right-hand side the Lagrangian. it's a function of x, our primal variable, and our dual variables u and v. And it always lower bounds the criterion function as long as x is feasible and u and v are feasible, which means that v must be bigger than or equal to 0. So Lagrange duality proceeds by saying that if C denotes the primal feasible set, so we denote C by the set of all x that satisfies these linear constraints, then the primal optimal value, the primal optimal value, f star, is equal to the minimum over all x in C of f of x. But we know that this is C transpose x, right? In our case. By construction, this is bigger than or equal to the minimum over all x in C of the Lagrangian, Lx uv, right? Because we said that for any u and v that are dual feasible, which means that u has to be anything and v has to be non-negative, we get this lower bound. So certainly minimizing over all x, it's still true. And this is further bigger than or equal to what happens if I don't just minimize over x that are satisfy the constraints, but over all x. If I make the domain of the minimization bigger, I still get a lower bound. And I define this to be equal to this quantity, GUV. So this is called the Lagrange dual function. Okay, and this thing is called the Lagrangian. So that's always true. In this example, right, let's just try to minimize this Lagrangian over all x. Right, what was the Lagrangian? Let's just write it out. Lxuv is equal to, let's rearrange it to get all the terms in x. I get A transpose U plus C plus G transpose V transpose X. And I also get minus B transpose U minus H transpose V. Just rewrote what I had in the slides. The Lagrange dual function is going to be equal to the minimum of this over all x. And we know that for any u and v that are u being anything and v being non-negative in every component, serves as a lower bound on the primal criterion. What is that? Well, first of all, what happens if this was not equal to 0? A transpose u plus c plus g transpose v is not equal to 0. Then we're asking to minimize a linear function with no constraints. So the minimum is just minus infinity. So it's minus infinity if A transpose u plus g transpose v plus c is not equal to 0. Otherwise, it's equal to minus B transpose U minus H transpose Z of V. That's the Lagrange dual function. To get the tightest lower bound possible, we're going to maximize this over all U and V. What does maximizing this all over all U and V look like? It exactly looks like this program. We've exactly derived the dual LP from a different perspective. Okay, that's Lagrange duality. We'll see that in detail next time. Go through that in general. The nice thing about that is that it works for general programs, not just for linear programs. Really, any problem you want to write down, convex or not, this perspective holds. We're going to study it in detail for convex programs. So that was it. We didn't have time to go over the matrix games example. It turns out every year I don't have time to go over this, so I actually feel like I've never gone over this example. Maybe we'll put it on the homework, but I really highly encourage you to go through it because this speaks to the history of duality. In some sense, this was the first instance of duality people know about. It came from von Neumann's minimax theorem. And it's a very interesting game theoretic consequence. It essentially tells you that it doesn't help if you know an opponent's strategy versus he knows your strategy. In either case, in this particular setup, kind of the expected payout that you're going to see is the same. If you know your opponent's strategy ahead of time or if he knows your strategy ahead of time. They seem like completely different scenarios in terms of how much information you have. But in this, what we call zero-sum games, this example, it doesn't matter. And that's another very interesting application of strong duality. And historically, this is what led to duality for linear programs, von Neumann's minimax theorem. Okay, so take a look at that. Maybe I'll put on the homework. I'm not entirely sure. Okay, I suppose we'll see you on Wednesday. If you want to stick around for a few minutes, I think someone ran out, one of the TAs ran out to get the homework, so they should be here in a minute. But otherwise, you can get them from Mallory's office anytime.